So looking at some of the AP problems, this is a calculator problem. So again, we probably won't have to do this in 2020, but we should take a look and at least understand how to set up the integrals for this. So we have a 20,000 liter tank of water filled to capacity. It looks like, it doesn't really say what the shape of the cylinder or the tank is, and we don't really need to know because they give you the rate at which the water flows out. So this is the derivative function here. So it's asking, the first part of the question is asking, is it continuous at t equals 5? Well, we need to check to see if t equals 5, the limit as t goes to 5 from the positive side of RT is equal to the limit as we come to the negative side. So let's check the positive side. It's going to 5, so it becomes 1000 e to the negative 1. Okay, so we end up with power negative 1, so we're just going to write it like that. And the limit as t goes to 5 from the negative side of r of t. Okay, we plug in the 5 from the other side. We end up with, that looks like 600 times 2, so 600 times 5 is 3000 divided by 2, or 1500. Okay, and these are not equal to each other, therefore not continuous. Okay, so for part B, the average rate at which the water is draining from the tank between t equals 0 and t equals 5 is going to be the area underneath R divided by the interval. So it's going to look like this. Okay, it's going to be the interval width and the area underneath the curve of R of t from 0 to 8. Okay, and that's going to be the average value of R, which is equal to the rate of change. Okay. We would have to integrate this, we'd have to, in this case, here we would have to use the integral. If we're integrating this, we wouldn't be able to integrate this because of this function here. We could integrate this, but this needs a calculator to integrate. So this is how, just setting up the integral would set it up like this. With a calculator, we'd actually solve those two different integrals. In fact, maybe I will just do that. Okay, so we're going to end up with 1 over 8. From 0 to 5, we are going to integrate 600 t over t plus 3 dt plus the integral from 5 to 8 of e 1000 e to the negative 0.2 t dt. Okay, and that would end up giving us the average rate of change. For part C, it says 5 r prime of 3 using correct units explain the context of the problem. So r prime of t, we would just have to first of all find r prime. Okay, we're going to do this from 0 to 5, so we're going to differentiate that expression. So that's going to be the rate of change of 600 t over t plus 3. Okay, we're going to differentiate that expression. It's quotient rule, so we end up with 600 times t plus 3 minus 600t times 1 all over t plus 3 squared. Okay, so that's our r prime of t for that interval. Okay, from 0 to 5 and equal to 5, I think. Okay, and then we should just simplify this a little bit because there are terms that cancel out. So we end up with 600t minus 600t. So we should end up with 1800 over t plus 3 squared. This is going to, we want to find r prime of t. as it goes to 3, so we need to use a limit here. So this is equal to r prime of 3 is equal to the limit as t goes to 3 of 1800 over t plus 3 squared. This is going to be 0. Okay, going from, doesn't matter which side because we're squaring it, it's going to be 1800 divided by 0, so we're going to get the slope is infinite. Okay, so it's got vertical asymptote. Okay, and this the units of this is going to be the change of the change, so it's going to be the liters per second per second. I think that's per second. No, sorry, liters per hour would be the rate of those units of that rate. Okay, and then the last part of this, part D. Okay, part D, it says write but do not solve the equation involving the integral to find time A when the amount of water in the tank is 9,000 liters. Okay, so the amount of water is, okay, the volume is equal to the starting amount, and I don't know if it gives us the starting amount. It starts at 12,000 liters, 12,000 liters, plus the rate from 0 to x. Sorry, I'm going to write from 0 to t. Okay, so volume as a function of time. Just be a little bit more clear about that. This is going to be v of t, and it's going to be equal to the integral, or the area underneath the rate curve, starting at 0 to t. Okay, so that's what it's going to look like. So to find the amount of water, the time A when the tank is 9,000 liters, we would have to first of all do the volume of the tank, and we could say that the time is A of r of x dt, and that's equal to 9,000 liters. We should really double check this in that if we were actually to write this in terms of the actual variables here, the actual functions, the piecewise function that we gave, we really do need to know the area under the curve, or amount, how much volume we lost in the first 5-second interval, and then because the function then changes after that as we're integrating along this. Okay, and so we could break this up into two pieces, into the first piece here, this piece here, and then this piece here like we did here, but we don't have any idea if the A is between 0 and 5 or the A is between 5 and or after, when t is bigger than 5. Okay, so if we were to split it up, we would have to figure that out. In this case, I'm just going to generalize it like this. We know that it's got to go from 0 to A underneath the curve r of x d of x, and this curve changes at